So where we left off in the last lecture, we were thinking about macroevolution as large-scale patterns in evolutionary change that are not fully explained by microevolutionary forces, the most important of which is natural selection, Darwin's mechanism. You see, natural selection is, for all the reasons we've been through already, a super important scientific theory, not the least of which is that it gives us a way of understanding how biological organisms have come to be so well equipped for whatever it is they do, and without the need for any supernatural causes. It's what makes biology a science, right? But Darwinian natural selection is limited in what it's able to explain. Changes within a population or within a species. When we're considering macro-scale evolution over geologic history, these fine-scale changes of microevolution are really on a different time scale from the patterns of macroevolution. If you look again at the horse example, we're looking across many species. What happens within a species may not be reflective of the broader pattern. And this is what seems to be the case when we actually look at changes occurring within and between horse species over the duration for which we have fossil evidence. It seems that we can't show that natural selection is causing increases in horse body size within species. So when it comes to the thing driving body size to increase over the multi-species history of horses over the Cenozoic, this explanation of microevolution, natural selection scaled up, leaves us cold. But then, if not natural selection, what is it that drives these observed increases in horse body size? Okay, I want you to stop here and realize that this is going to be another occasion in which it's more important that you understand the question than it is to know the answer. If you understand why we're asking this, then you're getting the picture of what we mean by macroevolution. Specifically, we may now need to look outside the domain of our four microevolutionary forces of drift, selection, mutation, and migration. Species selection. Think about a clade of horses all descending from Hyracotherium. You have 4 or 5 descendant species that arose, probably through events of allopatric speciation. Furthermore, each time a lineage splits, we end up with one species that's a little bit bigger in size than the ancestral species, and one species that's smaller. In other words, there's no bias towards larger size based on any microevolutionary changes. The two derived lineages differ in size from the ancestor, but not favoring either larger or smaller body size. From the German Shepherd-sized Hyracotherium, we have a bigger paleo horse, sized like a Great Dane, and a smaller paleo horse, sized like a beagle. So far, there's nothing that over the long haul would result in a general macro trend toward increasing size, right? But now, if it were also true that larger bodied species avoided extinction better and or they more easily underwent cladogenic, that is, splitting, speciation, then they will have more evolutionary descendant species at a later time relative to their smaller bodied counterparts. Over time, this would result in a trend toward increasing body size, even though natural selection within any of these lineages is not favoring larger bodies. You should note that this is actually similar to Darwinian natural selection, only instead of occurring at the level of differences between individuals within a population, it focuses on differences between species, and hence we call it species selection. This would be an example of an evolutionary force beyond the microevolutionary forces, and it is capable of accounting for the observed trend of increasing horse body size. All good? Okay, let's do this again with a similar example, but a different final lesson. Foraminifera. So foraminifera are tiny, single-celled, amoeba-like things living in the water, sometimes in great numbers, and they're very common in ocean water. They're single-celled creatures, as I mentioned before, but they also have shells. These are called tests that have different shapes for different species of foraminifera. We'll shorten this name to forams from here on. Now, in the pantheon of great fossil species, you've got those you probably think of right away. T-Rex, Apatosaurus, maybe some of the hominid fossils that you hear about a lot, like Ardipithecus. These are the remains of big vertebrates, and we are big vertebrates, which probably explains our fascination with them. These fossils are precious because they're rare. If you're a terrestrial animal, there's just not a very great likelihood that any part of your physical body will become a fossil. Fossils of things like clams are far more abundant. For one, because they have a hard shell that will resist rotting away, but also because they live in the water, so the remains are actually pretty likely to get covered by sediments and incorporated into rock strata. But an even better kind of organism to study, because their fossil record is likely more complete even compared with clams, are things like forams, because their shells actually make up the sediments that form the matrix of the rock. These microscopic fossils are there in abundance. From a small hunk of oceanic limestone, you might get thousands of tiny foram shells, usually smaller than 1 millimeter in their longest dimension. And because of their characteristic shapes, you can identify them to species. Yeah, you need a microscope, but you have no shortage of fossil samples. Vertebrate paleontologists are envious of you for your embarrassing wealth of fossil data, and also perhaps because you make a lot more money than they do. It turns out that these microfossil producing life forms have a practical use. They help us determine the age and provenance of the sediments, which means that they're very useful for things like oil exploration. If you're a fossil foram expert, you could be working for Exxon. This is as good of a time as any for us to talk about how we determine the age of fossils. It's really a matter of determining the age of the layer of sediments in which the fossils are embedded. Sometimes we can do radiometric dating of the fossils themselves. If you watch crime shows, you might be aware of radiocarbon dating. This is based on the slow decay of carbon-14 into nitrogen-14. While alive, we have a predictable proportion of the unstable carbon-14 isotope relative to the total amount of carbon in our bodies. If you found carbon-containing remains of the original animal or plant's body, you could tell how long ago it died by seeing how much of that carbon-14 is still left. This only works up to a maximum age of around 50,000 years, because by that time, all of the carbon-14 is gone. So for older samples, like most of the fossil species we'll be thinking about in BIO202, radiocarbon dating is not appropriate. The carbon isotope ratio for a 200,000-year-old sample would not be distinguishable from that of a 2 million-year-old sample. Fortunately, there are other methods basing their estimations of age on radioactive substances that decay more slowly than carbon-14. Uranium-lead dating and potassium-argon dating are particularly useful and have high degrees of precision for samples older than what we can age using radiocarbon methods. The problem with these methods, though, is that the elements needed are not usually going to be found in the fossil remains themselves. However, layers of volcanic ash or lava flows can be precisely aged, and so the age of a sedimentary layer can be constrained by the age of the ash layers above and below it. And here's where the forams come into great use. Sometimes we don't have layers of volcanic ash to give us reliable ages. But if we find forams and other microfossils together with an otherwise unageable fossil, and if we know the ages of those same forams from other locales where we do have volcanic ash layers to age them, that's all we need. We can presume that our unageable fossil is the same age as those forams. This is how index fossils are used in paleontology. Forams are among the most useful of microfossils. As I mentioned before, the oil industry relies on them heavily for identifying sites with high potential for yielding fossil fuels. This also means that we have a very complete knowledge of the fossil foraminifera that have existed throughout the last 500 million years. If you are asking yourself why anyone should put so much effort into describing the detailed shell anatomy of hundreds of species of ancient and now extinct marine zooplankton, well, this should give you your answer. So, if I tell you now that we know a great deal about fossil foraminifera with descriptions of hundreds of species, including when they existed and how big they were, you'll say, oh yeah, that makes a lot of sense. And if you're expecting to see Cope's rule being supported by these data, you might plot out the size of the tests, shells that is, against time, and you see a pattern like this. Well, you're telling yourself, this is just more evidence in support of Cope's rule. It's even true for zooplankton. And if Cope's rule is as true for foraminifera as it is for dinosaurs, then there must be something to the idea that bigger is better. Perhaps it's a general rule holding across the great expanse of taxonomic diversity. Well, that's kind of the way things were for a long time. Cope's rule became Cope's law to some people. Edward Drinker Cope had a loyal fan base in the paleontological community despite his being a repugnant and racist asshole. Then came along Stephen Jay Gould. In his book, Full House, The Spread of Excellence from Plato to Darwin, he presented a different interpretation of these same foraminifera data. As we look at the size of foraminifera as it changed over the Cretaceous, 140 million years ago to 65 million years ago, we see that the average size taken across many taxa increased. Gould did not dispute the fact of increasing average size. What he challenged was the idea that this increase was driven. In order for there to be a general truth behind Cope's rule, there must be something that favors larger bodies over smaller ones. It could be natural selection, or as we discussed for the horse body size example, it could be something like species selection, with a larger bodied species being more likely to persist and not go extinct and give rise to more species. In either of these cases, the increase in body size is actually driven by directional force, natural selection or species selection. Gould argued that when you look at the foram data, the increasing average might be explained without any driving force at all. Look at where the history starts. The oldest foram species had a test diameter of 0.2 millimeters. This is practically right at the lower boundary of shell size. With the normal methods used for sampling microfossils, the material you get after dissolving the stuff between the shells, this material is passed through smaller and smaller sieves. And it's possible that the paleontologists didn't even look for microfossils smaller than what their finest sieve could capture. And even if we could include the smaller foram species, you really can't get that much smaller than the starting foram because there's only 0.2 of a millimeter between this starting point and zero. And somewhere in between, there must be a hard boundary for the minimum possible size. Foram size evolution in the downward direction is highly constrained, while evolution toward larger size is not so constrained. Now, there may actually be an upper limit to the body size for foraminifera, but it's not as rigid and not nearly as close to the starting point as the lower limit. This, I think, is entirely reasonable. Gould then posited a history of foram body size evolution, starting at 0.2 millimeters and changing by tiny steps in a random direction, like we did in our earlier example with increases and decreases occurring with equal likelihood. In this case, foram size evolution is unable to drop below the minimum body size, so lineages that happen to increase are free to evolve increases, but those that are close to the minimum and happen to decrease bump up against a reflective wall, and they aren't allowed to evolve sizes smaller than the minimum possible body size. And so what you end up with is an overall increase in average body size across all 4M taxa, and this would happen without anything driving evolution towards larger size. So now we have two competing hypotheses to explain the pattern of increasing average size of foraminifera. One is the traditional view based on there being a general rule, Cope's rule, that says increasing body size is favored by evolution. Gould's alternative explanation is based on, well, no driving forces at all, just random change, but from a starting point that is very close to the minimum. Which of these two hypotheses is more parsimonious? I hope you said Gould's model. The traditional view requires something that forces body size towards increase. Natural selection or species selection, or maybe something else that we haven't discussed. If this is the case, then the size increase is a driven trend. Gould's model requires nothing driving size evolution. A starting point close to the minimum is given, and random evolutionary change presumes no underlying directionality in the way that the traditional model does. If we apply the principle of parsimony, Gould's model, the one with no driving force, would have to be the preferred explanation of these two. Does this mean that Gould's model is correct? Well, no, not necessarily. Remember that we can't count on the most parsimonious explanation to be the correct one unfailingly. Sometimes the more complex explanation is closer to the truth. Now think about this. Is there any way to investigate further which of these two models is supported? Ancestor-descendant pairs. Sometimes when you have very good fossil data like what we have with the 4Ms, you can, with fairly high confidence, draw a direct line between an ancestor species and a descendant species. This one over here and this one over here have very similar shapes and are different from all the rest. And so from this, you can presume that the later one is the descendant of the earlier one. If you were to draw in all the lines connecting ancestors with their descendants, is the slope of that line usually inclining? Because if there were a systematic favoring of evolution towards larger body size, you would expect a bias in favor of increasing size, more lines sloping upwards than downwards, increases greater than decreases. But with a non-driven Gouldian alternative, there would be no tendency to either increase or to decrease. So you would expect lines sloping upward half the time and sloping downward half the time. Increases equal to decreases. Can you see the rationale here? These two models make distinct predictions that, at least in theory, can be evaluated with the data that we have available. For those of you who opt to write on the Churchill et al. Paper on pinniped body size evolution, you'll want to keep this in mind as you're reading that paper. Okay, let's apply this same logic to a different evolutionary trend that's of greater significance than the size of foraminiferan tests. Ask yourself, has there been a trend toward increasing complexity in the evolutionary history of life? Most of us would quickly nod our heads and say, of course. Initially, the only forms of life were bacteria-like, tiny and unicellular. And then later you had primitive multicellular forms like sponges. And then more complex things like worms came later. Fish, even more complex, came later still. And still later are more complex things like lizards and mammals. The fossil record supports this. Now, it's a difficult thing to quantify complexity on a fine scale, such as between the individuals in a population. For example, is Susie more complex or less complex than Jeff? Is not something that we can answer too easily, but surely we can agree that worms are more complex than sponges, fish more complex than worms, etc. And if you were to go back to the Earth of 3 billion years ago and assess complexity for all forms of life in existence, you'd have a narrow range. everything is bacteria-like, and though you have some simpler and some more complex, there's nothing even approaching the complexity of a sponge. If you were to do the same for 300 million years ago, the range would be much greater. Bacteria would still be there, but you'd also have sponges, worms, fishes, and even lizards. No mammals yet, they come later. Now, do the same thing for the current array of life forms on planet Earth, and you'd have the full range from bacteria to mammals, including our species. And I could mount a pretty decent argument to say that we are the most complex mammals that have ever existed. But now we have to plot the relative frequencies of life forms at the various levels of complexity. 3 billion years ago, this might have looked like a symmetrical bell-shaped distribution. Now, think about today. What is the most common form of life on the planet today? Well, it's bacteria and archaea. These are in the same group that are referred to as bacteria-like before. They are far, far more numerous, diverse, and collectively massive than any other form of life. And so they occupy the node, the high point of our frequency distribution, with a long, long tail extending way to the right. Now, I'm certain that for the life on Earth 300 million years ago, you'd have the same basic shape, just not extending as far to the right. It's no joke to say that bacteria-like things rule the Earth today just as they did 3 billion years ago and every moment in between. Stephen Jay Gould called this the modal Bacter, and he pointed out that the representative life form on planet Earth is and always has been a bacterium. Sure, the most complex life continued to increase in complexity, but the average stayed where it always was, the modal Bacter. Do you see the parallels with our foraminiferan evolution example? What would you expect to happen if you started out 3 billion years ago, close to the minimum possible complexity, and then evolved randomly, that is, with increasing complexity and decreasing complexity occurring with equal frequency? Wouldn't it look something like this, with a modal organism staying pretty close to the starting point, but with one tail of the distribution stretching out to extremely high levels of complexity? If you had to pick one organism to represent life on Earth today, what would you choose? Would it be a mammal or bird? If you had to do the same from 100 million years ago, would it be a big scary dinosaur? 300 million years ago, would it be a fish? Gould's point hits a nerve. When do you ever use a group's most extreme member to be its representative? The modal Bacter has rightly been the representative of Earth life at all times since life's origins. The fact that humans are both large and extremely complex has rendered us somewhat less than objective in thinking about macro-scale trends. Might we not be inherently inclined to think that evolution has favored larger and more complex things over smaller and simpler things? I ask this rhetorically. Again, if you understand what I'm getting at here, we don't need to actually answer whether or not evolutions of greater body size or greater complexity is driven. If someone brings this up in our live meeting, though, we can talk about what the evidence tells us. Let's look now at a form of evolutionary change that is, without question, beyond the scope of the microevolutionary forces that we talked about in earlier lectures. In the 1980s, Dave Raup and Jack Sepkoski of the University of Chicago completed the remarkable task of compiling data from the fossil record of every taxonomic family of marine animal ever described. Specifically, they took note of the age of the earliest representative fossil, when it first appears in the fossil record, and the latest representative fossil, when it went extinct. Based on this information, they were able to report the total number of all families of marine invertebrates and vertebrates at any time from 600 million years ago to the present. Their results validated what paleontologists had known for a long time, that there had been mass extinctions, recurrent biodiversity crises, during which there was a lot of extinction occurring over a very short period of time. With this famous graph, Raup and Sepkoski identified what came to be known as the Big Five extinction events, occurring in the late Ordovician, the late Devonian, late Permian, late Triassic, and late Cretaceous. Two of these, the late Permian and late Cretaceous events, mark the boundaries between the eras of the Phanerozoic, which is the last 541 million years, or the time for which we have a reasonably good fossil record of animals. We'll be covering the geologic timeline in later units. Important here is the knowledge that life has taken a few big hits, the Big Five plus a few others, at which time a large proportion of animal diversity was lost. By the way, the percent losses for species are far greater, far more dramatic than what you see in this figure. Why? Well, in order for a whole family to have gone extinct, this required that all of the genera and all of the species belonging to that family went extinct. If a taxonomic family were to have 10 genera and each genus had 10 species, then the loss of that one taxonomic family would mean the extinction of all 100 species, because if even one species from that family were to survive, then the family would not be extinct. So, if at the end of the Permian there was a loss of 52% of taxonomic families, at the species level, it must have been near total devastation. Raup estimates that as many as 96% of all animal species might have gone extinct. Just a bit worse than that, and all animals would have gone extinct, including your ancestors. And the history of life on Earth could have taken a very different path. Now, in between these mass extinction events, life's diversity increased. It had to. If nothing were to counteract the losses in diversity, then the total inventory of different forms of life on Earth would dwindle down to nothing. Sometimes these increases in diversity were pretty spectacular, with a steady and high rate of new taxonomic families appearing in the fossil record. But it could never match the speed of change of mass extinctions. Extinction could take place in an instant, like when that space rock smashed into Mexico 65 million years ago, wiping out most of the dinosaurs. Speciation, as you know now, is a process usually requiring geographical isolation and lots of time. Now, sometimes it can go faster than others. These faster periods of increasing taxonomic diversity coincided with times when life was bouncing back in the aftermath of a major extinction event. One key pattern I hope you're seeing here is that it's not just new forms replacing old forms. Earlier, we called this anagenic evolution. This view from 30,000 feet, though, shows us that the total diversity of life forms has increased and decreased. Life itself is becoming more diverse and less diverse over time. What causes this kind of evolutionary change? Well, the thing causing the decrease is extinction. Now, there's one thing that students sometimes miss when we have this discussion. It's that species extinction, the dying out of every last individual of a species, is something that occurs all the time throughout the history, not just at the mass extinction events. It's like the dynamics of a population. Individuals die all the time, but that's largely compensated by births of new individuals. And if the birth rate and death rate are balanced, the population size is relatively steady. Likewise, extinction of species happens all the time, and it's largely balanced by an opposing force that's akin to the birth rate of individuals in a population, the one that compensates for death. Species have finite lifespans. They originate, stick around for a bit, and then disappear. New species originations are like birth. Extinction is like death. Neither ever drops to zero, but they can be out of balance. If new species originations occur at a faster rate than extinction, then the species count increases. So even in the times between mass extinction events, there is extinction that is largely compensated by new species originations. What makes these mass extinction events special is that the rate of extinction spikes to far outstrip the rate of new species originations. Now, what is the cause for new species originations? You should have the answer for this pretty quickly. Remember speciation? What was the other word for this? Clado something? Yes, new species origination and cladogenesis are effectively the same thing. Again, to have an increase in the total number of species, what you need is for the speciation rate to be greater than the extinction rate. If they're exactly balanced, then no change in species number. If speciation is somewhat higher than extinction, you have moderate increases in species count. If, like during a mass extinction, the extinction rate spikes to extremely high levels because of space rocks or cataclysmic volcanic eruptions or some other cause for carbon to be spewing into the atmosphere, then you could have speciation being completely overwhelmed and there will be a dramatic loss of biodiversity. Do you see how the forces at work here, the things causing changes in this graph, cladogenic speciation and extinction, are not directly related to microevolution? This is why we're talking about it here in our macroevolution lecture. And after the break, we'll take on the next item on our macroevolution focused agenda.